Okay, let's take a look at this example. We want to find Ix, the current Ix, which is coming down through this capacitor, using nodal analysis. And of course we're doing this and we're going to do this in frequency domain. So the first thing you want to do is want to take this circuit and convert it to this circuit, okay, to go to frequency domain. So you want to take that circuit and go to frequency or phasor, okay. And then we're going to do the standard nodal analysis we've been doing throughout the examples we've been doing throughout the semester. Okay, so first thing we do, we take our voltage source, which is 20 cosine 4t, and we convert that, put it in polar, that's 20 at an angle of 0, and we make a note that our omega is going to be 4 radians per second. Our inductor, 1 Henry, is going to be J omega L, which equals J4. Again, omega is 4, L is 1. Our other inductor is 0.5 Henry. Again, we're going to do J omega L, and it's going to give us J2. Now we have the capacitor, which is 0.1 farads, and that's going to be 1 over J omega C, which gives us minus J 2.5. Okay, so going from this 1 Henry becomes J4, it's going to be here, J4, J2 here is going to be coming from here. I'm going to highlight 1 Henry, and then our capacitor, which was here, is going to be minus 2.5. Everything else stays the same. Of course, the source voltage is going to change as well. We're going here, here to here. The resistor stays the same. So now we've converted into a frequency domain equivalent circuit. Now we're just going to apply Kirchhoff's current law. So let's go up here. Using this circuit now, we're going to apply Kirchhoff's current law. KCL at node 1. Which is going to be this point here. And what we get is 20 minus V1 over 10 is equal to V1 over minus J 2.5 plus V1 minus V2 over J4. So what goes in equals what comes out. And then we can rearrange this equation, and we come up with 1 plus J 1.5 V1 plus J 2.5 V2 is equal to 20. Alright, so let's hold on to this equation here. We're going to use this to come up with our final solution. Okay, now let's look at node 2. At node 2, right here, we get 2 Ix plus V1 minus V2 over J4, okay, is going to equal to V2 over J2. Now we know that Ix equals V1 over minus J2.5. So we can substitute that. We can substitute this guy in here. And if we do that, we can rewrite. We can rewrite this here. We get 2V1 over minus J2.5 plus V1 minus V2 over J4 is equal to V2 over J2. And then we can simplify this, and I'm going to write it over here. We simplify, we get 11 V1 plus 15 V2 equals 0. And then we're going to use this equation in combination with the other equation to come up with the final solution. Now there are a couple ways to solve for this. We can use Cramer's rule, or we can just do old-fashioned substitution. So I'm going to do the old-fashioned way, which is a little bit longer but a little easier to see. Again, it's your choice which way you want to apply this. So let's go ahead and combine the two equations we came up with. And if we do that, let's just say I'm going to rewrite this guy in terms of V2. It's going to give us minus 11V1 over 15, and I'm going to substitute this equation into here. If I do that, scroll up, I get 1 plus J 1.5 V1 plus J 2.5 times minus 11 V1 over 15 equals to 20. Okay. Now we can simplify this several different ways, but let's just go ahead and take it step by step. One plus J 1.5 V1 minus J 27.5 over 15 V1 equals 20. 1 plus J 1.5 V1 minus J 1.833 V1 equals 20. And now we can combine the imaginary parts. We get 1 plus J 0.33 V1 equals 20, and then that gives us V1 equals 20 divided by 1 plus J 0.33, and then it's just a matter of converting to the format that we prefer. Again, if you want to simplify this, we can multiply the numerator and denominator. Actually, I made a mistake here. This should be a negative here. This should be a negative. So this should be a negative here. This should be a negative. Okay. And then we just multiply the numerator and the denominator by the conjugate of this. So if we go up here, so I got 20 over 1 minus j 0.33, and then we're going to multiply the numerator and the denominator by 1 plus j 0.33. That's going to give us 20 1 plus j 0.33 over 1.111. Okay, and rewrite this some more. In the numerator we get 20 plus j 6.66, and then denominator we got 1.111, and that's going to be approximately 18 plus j6. Okay, so we got approximately 18.j6. So this is going to be our V1. Now this is in rectangular format. If we wanted to put it in polar format, so this is, we can highlight this here, rectangular. Let's go to polar, and to do that we just say 18 squared plus 6 squared is going to equal to approximately 18.97, and then our theta is going to equal to tangent inverse of 6 over 18, and that's going to give us approximately 18.43 degrees. Okay, so our V1 in polar format is 18.97 at an angle of 18.43 degrees. Okay, and now we can substitute this back into the previous equation. So we know that we can take this V1, either this one or this one, and plug it back in here to get V2. Again, your call, your choice on how you want to do this. I'll just do it one way. Okay. So we got, whoops, V2 is equal to minus 11 over 15 times 18 plus j6. Okay, that's where we plug in our V1. So we work this out some more. We'll go sideways here. We get a minus 11 times 18 over 15 plus j 11 times 6 over 15, and that's going to give us minus 13.2 plus J 4.4 for V2. And then we can distribute the negative in here, so minus 13.2 minus J 4.4. So this is our V2 in this format. And then we can do the same thing, put it in polar form. So we get our magnitude is going to be, we're going to have minus 13.2 squared plus minus 4.4 squared. That's going to give us roughly 13.91. And then we do our angle tangent inverse y over x minus 4.4 over minus 13.2, and that's going to give us roughly 18.43. So 18.43, and we can add that. So if we look here, we can write this in two different ways. So a couple things to note, because both the real and negative, both the real and positive imaginary parts are negative, the angle is going to be in the third quadrant. Okay, so instead of 18.3 degrees, it's going to be 18.3 degrees, 430 degrees plus 180 degrees, and that's going to give us 198.43 degrees. So then our V2 is going to equal to 13.91 at 198.43 degrees. Okay, and the reason for that, I'm going to make this note, both real and imaginary are negative. They're negative, meaning we are in the third quadrant. Okay. So now we have V1 and V2 in terms of polar coordinates, but now we still need to figure out our I. Okay, so our I is going to be Ix is equal to V1 over minus J 2.5. We just plug these in here. We said this was 18.97 at an angle of 18.43 degrees over minus J 2.5. Okay, we can convert this back to rectangular format and do that work again, or we can take this guy and put it in polar format, and what that gives us is 2.5 at minus 90 degrees, and work in that format. And if we do that, we get 7.59 at an angle of 108 degrees. 8.4 degrees, and this is going to be in amps. Okay, these guys were in volts up here, so that's going to be in amps. So we have our I over here in polar form. Now if we were going to do this in the rectangular format, we would have to, because we would have to switch the add another 180 to these, because you're going to be in the second quadrant. Okay, so this is what we get for I, and then of course we can take this and put this in time domain. I x of t is equal to 7.59 cosine, our omega was 4, so 4t plus 108.4 degrees amps, and this is our final answer. So again, the math isn't complicated, it's just a little cumbersome, and it really depends on how you approach this problem. If you're going to be converting to rectangular format or keeping it in polar format, or going back and forth, it really depends. Or if you want to solve using the old-fashioned way, which is the approach I chose, versus using Cramer's rule, which is a much shorter way of doing it, like linear algebra approach. Okay, so I just want to show you this long method just so you can have that in comparison to the linear algebra solution. So that's how you solve this problem.